So hi everyone. Minor logistical thing that I should start by mentioning. Midterm 1 will be happening next Tuesday. The format will be that it's 1.5 hours, but you don't have to be around during lecture time if you're in the wrong time zone or whatever. So you will be able to take it anytime within those 24 hours via Gradescope. What other points? So it will cover everything from lectures 1 to 6, so homeworks 1 to 3. But generally, it's going to be about, it's going to be quantum mechanics, unitary gates, unitary circuits, measurements, entanglement, stuff like that. So it's all, it's not going to be about particular details or things that are covered in the lecture. It's going to be testing, like, have you got comfortable with how quantum mechanics works and how the formalism works, and able to do a variety of problems on that. Will be open book, just because I think trying to make it closed book and asking you guys to honor code is possibly a mistake. But yeah, no working with each other. Please do it on your own. What else is there to say about that? I think that's basically everything. Any further questions people have, clarifications and so on, just ask on Piazza. Give you more details near the time as and when they exist. But yeah, that should do for now. Okay, so on to the lecture. So last time, what did we talk about? Well, we introduced the idea of complexity classes for both classical and quantum computers as the classes of problems that can be solved using some certain amount of resource. Maybe that's a certain amount of time. For example, polynomial time for classical computer is called P. Exponential time is called exp. But it could be limited to a certain amount of space. That's P space, polynomial space is a good example. Could be about whether they can be verified in a polynomial time. That's NP. Could be whether they probabilistically solvable in polynomial time. That's BPP, which is thought to be pretty similar or possibly even the same as P. And finally, there's sort of the quantum computing analog of BPP, which is BQP, which is what a quantum computer can solve probabilistically in polynomial time. And we talked a bit as well about how BQP is defined. And basically, you need to define it using some universal gate set, some set of simple gates that can be used to approximate any other gate. So for example, the Hadamard, the pi/4 phase gate, also known as the C gate and the C0 gate, being able to apply them to any qubit or pair of qubits is enough to eventually approximate any unitary you want. But we also noted that the definition of BQP, because things only have to be approximate, is actually independent of the details of your choice of universal gate set. So that's why we normally talk about BQP rather than what's sometimes called EQP, exact quantum polynomial time, because EQP depends in very detailed way on exactly what your set of gates is. Okay, so today, first thing I want to talk about is going to be using quantum computers to do classical algorithms, and in particular showing that any classical algorithm that can be done on a classical computer in polynomial time can also be done on a quantum computer in polynomial time. Okay. And then after that, we're going to move on to seeing things that a quantum computer can do that a classical computer can't do. So these are sometimes called quantum speedups. We're going to see our first two examples of them today, which are going to be a particular class of examples called examples relative to an oracle. See what that means in a bit. And they're called Deutsch's problem and the Bernstein-Vazirani algorithm. Okay, so let's start with trying to argue that anything a classical computer can do, a quantum computer can also do. Note that we're assuming that the quantum computer is able to apply the same number of gates and has the same number of qubits as the classical computer has bits. This is obviously not a realistic assumption with current state of technology in either field, and almost certainly never will be, right? Classical computers will always have vastly more bits than quantum computers have qubits. But, given given that they're the same, we want to show that anything a classical computer can do, a quantum computer can also do. Okay. So what we need to do is show that the sort of basic gates that we use for quantum computing, for classical computing, can also be applied on a quantum computer. So there's various things you could use for that. You can just use a NAND gate, for example. But a natural pair of gates to use that are universal is a NOT gate and an AND gate. Okay, one of these two things you guys should know already how to do on a quantum computer. Anyone want to say which one it is and how you do
it? We know how to do NOT with the X gate.
Yep, awesome. So NOT gate is very easy to do. You just have some qubit that we're just going to assume is either ket0 or ket1. Not going to worry about superpositions. And we just apply an X gate to it. Okay, and that applies a classical NOT. What about AND? So what would it mean to do an AND gate? It would mean you'd have some gate that we'll call U AND, and it takes in two classical states, we'll call them A and B, and then we want output to be A times B, A and B, and then I guess our other qubit is going to be in some state. We'll just call that some state psi. Don't know what that is. Okay, that's what it would mean to have a unitary gate that does a classical AND. So it's actually a problem on homework 4 to show that this is impossible. There's just no, well, what we actually show in homework 4 is that there's no classical psi. So let's make this psi could in principle depend on A and B. There's no psi, no function of A and B such that this map from AB to A and B plus psi is invertible, right? If it's not invertible, then we can't turn it into a unitary. So we seemingly can't do an AND gate. So that's a bit problematic. I thought, I said we could do classical computing. Anyone know the loophole we use to get around this? Anyone have any ideas for what we might try to do? I'll give you a clue. At the moment, we're just thinking about gates acting on only 2 qubits.
You can use ancillas.
Awesome. So What about if we instead want to have some unitary for doing AND, where we have A as an input, we have B as an input, and we have some third state that we can assume is in the 0 state, right? Now, we can imagine that the output of this just leaves A and B alone, leaves the first 2 qubits unchanged, but the third qubit gets mapped to A and B. Okay, this is perfectly reversible. It's easy to check. It's a unitary gate, and in fact, it's a unitary gate that you've seen before, I think on last week's homework, which is called the Toffoli gate, or sometimes CC not. And it's written as a circuit like this. So what does this do? If and only if both the control qubits are 1, right? If and only if A is 1 and B is 1, then it applies a NOT gate to the third qubit. So this goes to A, B, C plus A times B. Okay, so if we just have our third qubit C start in the 0 state, then we can do our AND gate. But of course, we still have original A and B there. But you know, if we want to do some classical circuit, one sort of very naive approach is to just use a new qubit to store each like new output bit, each, I call it intermediate output bit. So say we want to say we wanted to compute A and B and C, right? Or to make it, you know, put some unnecessary brackets in there, we want to compute A and B, and then the AND of that with C. So one way we could do this is we just want to compute A and B. So we apply a Toffoli gate, stores A and B in this ancilla qubit, and then we want the AND of that with C. So again, we just store it in yet another qubit. And finally, so the final state this would still be A, this would be B, this would be A and B, this would be C, this would be A and B and C. Okay. So, you know, that works. That lets us do anything in P using stuff in BQP. Great. But it's really quite inefficient, right? We're using a new qubit every single time. We're ending up with all these, you know, all these qubits that are sort of, end up in states that depend on our initial inputs, A and B. What would be nice is to be able to, you know, say this qubit in the middle that was computing A and B, once we've computed A and B and C, let's say this is some part of some larger calculation, we might not care about A and B at all, we might just want to erase it, right? And if we could erase it, then we can, yeah, if we can erase it, then we could use the qubit again, and we don't need an extra qubit for every single step in the calculation, right? So, yeah.
Quick question. So I'm wondering, does this gate only works if A, B, and or A and B are in the standard basis?
Yeah. So I'm assuming here we're doing some classical computation, and so we've prepared the states A and B. You know, A and B were originally like classical inputs, and we've then coded them as qubits in the 0-1 basis. So we're not worrying about what this circuit does to superpositions for the moment. Okay. So rather than just constantly using new qubits, new qubits, new qubits, it's helpful to erase intermediate bits. Of course, we can't just apply some unitary to this qubit A and B to take it to the 0 state, because that's not a reversible map, right? You can't take everything to 0 and have it be a unitary. So what do? It's very simple. First step is you copy your final answer into a clean qubit, right? So some ancilla. So this we just use a C0. We apply, so we have A, B, A and B, C, A and B and C. Okay, so the first step is we just apply a C0 to store our final answer in a completely clean qubit that hasn't been used at all. Okay, so now this bottom qubit is A and B and C, and everything else is unchanged. And now we're going to try and erase everything, all these intermediate qubits. So we're going to try and erase this qubit and this qubit, and just get back to everything in the 0 state except for our original inputs A, B, and C. Anyone know how we do that?
Do the circuit backwards.
Awesome. So we know a unitary circuit that takes A, B, 0, C, 0 to A, B, A and B, C, A and B and C. So all we do is apply the dagger of that circuit so where this whole thing is calling U. Okay, so we're just applying the reverse of that whole circuit that we applied before. And that will take us to a state where we've erased all of our intermediate qubits, and we just have the final answer and the original 3 qubits. Okay, and then we want to do some further computation that uses A and B and C and maybe some other stuff. Then we can do that, and we can reuse the ancilla qubits that we erased. Okay, so step B is just reverse the original circuit. So in the textbook, so in Riefel and Pollock, chapter 6, they go through in a lot of detail. Any computation using pretty small time and space overheads compared to the classical computation. They're both basically logarithmic in size of the circuit, original classical circuit.
How was the taking the A, B, and C to a copy of itself not a violating of the no cloning theorem? This should
yeah, because this is we're taking the classical A and B and C to a copy of itself, right? So that's just a C naught gate. So if I have, right, if the C naught of x0, where x is 0 or 1, is equal to x. So seemingly we've done a copy, but C naught of, say, plus 0 is not equal to plus plus. It's equal to the bowl state, phi plus.
Okay, thanks.
Right. So yeah, that copying the classical bit stored in a qubit is allowed, but not the quantum state of the qubit itself. Okay, so it's going to turn out in the later algorithms we see. So final comment. Raising the intermediate bits isn't just a thing to speed things up a bit, or to reduce the space overhead even. It's going to be very important when we get to quantum algorithms. Where we put in the inputs in superposition. The reason for that is if you don't erase your intermediate bits, then they will be entangled with the bits you care about. We'll see an example of that in a bit. Okay. So that's all I'm going to say about using quantum computers to do classical algorithms, because frankly, that's a very boring thing that nobody would ever do. We have classical computers for that. They're much better at it. They have a lot more bits. They can apply a lot more gates. Now we're going to start talking about things that quantum computers can actually do better than classical computers. But the things we're going to see today are going to be nice in one way and not nice in another way. They're going to be nice in the sense that you can actually prove that quantum computers are faster. But they're going to be less nice in that they're going to be what's called relative to an oracle, which means they're going to have involve some black box. Yeah. So they're going to involve what's called query complexity. Which is basically a game where you're trying to minimize the uses of some black box, i.e. unknown, like you're able to use it, but you don't know how it works, or oracle function. Okay, So this is different from just the ordinary definition of computational complexity, where you're just trying to do some algorithm that just takes you from the input to give you the output as fast as possible. The next 3 or so lectures will be speed ups with no oracle, but also not provable. Okay, it is not known that for just general computational complexity, it's not known for sure that quantum computers can actually do anything classical computers can't. There's things we know how to do on a quantum computer that we don't know how to do on a classical computer at the same time. Factoring, for example, can be done in polynomial time quantum computer. We have no idea to do it on classical one, but nobody knows how to prove that you can't do factoring fast on a classical computer. Okay. Okay. So maybe unclear at this point what I mean by this black box oracle function, but what I'm going to do is just going to dive in to our first example of Deutsch's problem. And we'll sort of see how it works as we go. Okay. So Deutsch's problem, our oracle, is going to be a function that just takes 0 or 1 to 0 or 1. And our question is going to be, is f of x constant? I.e., does f of 0 equal f of 1? Okay. And we want to work out whether this is true by using this function as a black box, but using it as few times as possible. So we say I'm going to use the function with input 0, for example, and then the black box will go, okay, the answer is f of 0 equals 1 or 0, whatever it might be. And then we can also do the same thing with 1. And I think it's pretty clear that for the classical version of this problem, we need 2 calls of the function f to answer the question. Right, we first need to ask, input 0 and see what it spits out. And then we need to input 1, see what it spits out. And then we need to see whether those 2 things are equal. If you only have done one of them, then you have no idea about the other one and you can't tell whether it's constant or not. What about the quantum mechanical version of this? Well, the first thing we need to do is define what the quantum mechanical version of the problem is, right? We've got to say, that at the moment, this is just a classical black box where we input either 0 or 1, it returns either 0 or 1. What we want to do is upgrade that to a quantum black box, okay? And by analogy with how we were using quantum computers to do classical calculations above, the sort of natural definition of a quantum black box is the following. It's that we have some unitary that depends on the function of f that takes in x and y, okay? And it outputs just x unchanged and y plus f of x mod 2. Okay, so if y equals 0, then it just outputs, leaves x unchanged, so that it's actually a reversible function, right? There's no unitary that just takes x to f of x if f of x is constant. So there's the only thing you can do is have the unitary, have f of x be stored in a second qubit. And then to make the whole thing unitary, it can't just be, it also needs to depend on what that second qubit was, right? What y was. And so the natural thing to have is that it goes to y plus f of x. Okay, this is exactly what we would have had with our previous algorithms, right? If we'd put y here rather than 0, we would have y plus a and b and c. Okay. So I want to emphasize that we now have a different problem. Okay, this is not that a quantum computer can do the same problem as a classical computer faster. This is there is a problem involving a classical black box that you can do in a certain amount of time, and then there's a problem involving a quantum black box that takes a different amount of time. However, with those provisos, the claim is that we can solve the quantum problem with only one call of UF. Okay, so classically we needed to look at it twice. Quantum mechanically, once is fine. Okay, how do we do this? Well, we do the usual trick, which is we're going to input it to not some classical state 0 and 1. Clearly, we can't do anything with that. We're going to instead input a superposition over the two. And in fact, what we're going to do is we're going to apply U of f to first qubit in state plus and the second qubit in state minus. Okay. So what happens to that state? Well, we've got four things, for a superposition of four sets of 0 and 1. Okay, so we have a half times input 0, 0, U of f 0, 0, which is 0, f of 0. And then we have U of f acting on plus U of f acting on 1, 0. So that goes to 1, f of 1. And then we have minus U of f acting on 0, 1. So that goes to 0, 1 plus f of 0. And finally, we have minus 1, 1 plus f of 1. Okay. Just the four terms in the superposition. Apply U of f to each of them. But now, let's note that we can rewrite this in the following way. This is just a half times a sum over x. X is either 0 or 1 times x times f of x minus 1 plus f of x. Right? Just condense the previous thing. Now, what we note is let's consider the two cases where f of x is 0 and f of x is 1. Okay, if f of x is 0, then this is just 0 minus 1. So that's just a minus state. If f of x is 1, it's 1 minus 1 plus 1 is 0. So it's again the minus state, but it's minus 1 times the minus state. Right? So this state can actually be written as a half, or actually 1 over square root 2, minus 1 to the power of f of x, x minus. Okay. Or more explicitly, 1 over square root 2. I'm going to take a minus 1 to the f of 0 at the front. It's just a global phase. 0 plus minus 1 to the f of 1 minus f of 0 times ket 1 times the second qubit just being in the minus state. Okay, someone tell me how I can now extract out the answer of whether f of 1 and f of 0 are equal to one another or not.
You measure x in the plus minus basis?
Awesome. So if f of 1 equals f of 0, then this first qubit is just in the plus state, right? 0 plus 1. If they're not equal, it's in the minus state, 0 minus 1. So in general, when we're doing quantum computing, we don't like to measure in bases other than the computational basis, but that's very easy to fix. I just apply a Hadamard to the first qubit. So then this becomes minus 1 to the f of 0, f of 1 minus f of 0 times minus state, right? We measure first qubit, and we're done. Okay, so again, make a couple of comments about Dodge's problem before we move on to Bernstein-Vazirani, which is going to be a bit more interesting. Again, I like regularly making the comment just because people have this weird intuition that it's never true. This is a deterministic algorithm, right? So we've got a quantum speed up. It will do something quantum mechanical faster than we could classically, but it's completely deterministic. There's no probabilities involved. The measurement always is just in the computational basis, and the state's in the computational basis. So we always get the right answer, assuming no errors. Second point is that the answer, again, this is a common theme, answer that we wanted, that we couldn't get classically, ended up being encoded in the control qubit, right? So when we applied this U of F, if you looked at what it did in the computational basis, it seemed to leave that first qubit completely unchanged. But actually, when you apply it to the superposition, then the first qubit is the thing that learns the answer to whether f of x is constant or not. Final comment is that if U of F was constructed by a quantum circuit, then it was vital that U of F erased any temporary qubits that were used in its computation. So let's just see.
Would you mind just saying why that's important?
Yeah, so I'm going to explain why that's important now. We'll just see that it doesn't work. Okay, so let's suppose instead that we had some V of F, okay, another unitary V of F that takes in X, Y, and Z. And output leaves X unchanged as before, okay? Z is going to go to Z plus F of X, sort of like before. But there's going to be some intermediate calculation that depends on x that's going to get left in this middle qubit, right? So maybe this goes to y plus x. We just accidentally made a copy of, applied a C0 copying x as part of the calculation, and then we forgot to get rid of it. Okay. Now we can look at what happens when we apply V of f to sort of the analog of the state before, right? So we have the output qubit in state minus, the input in state plus, and this intermediate thing just in 0. You can check. It's pretty easy to check, right? We just if y is equal to 0, then x just gets copied across so that we have 2 copies of x rather than 1. Okay, so now our final output is going to be -1 to the f0. First qubit is 0, but also the second qubit is 0. Plus -1 to the f1. Again, the first qubit is 1 as before, but we have the second qubit that is also 1. And then finally, as before, the last qubit will just be in the minus state, right? So what we see is that the temporary qubit because our input was a superposition over different x's, has become entangled with the first qubit. And that means that any measurement, these two things are maximally entangled, any measurement that we do on the first qubit will just give a random 50-50 answer. So if we apply the Hadamard, you can check that even if we apply a Hadamard and then measure in a computational basis, then yeah, we can't learn any information. If we had access to the first 2 qubits, we can still rotate the Bell basis. We could apply a C0 and then a Hadamard, and that would let us extract the information. But if we only have access to the first qubit, then we can't extract any information.
Can you just measure the temporary qubit first?
Good. So let's say we measured the temporary qubit in say the 0-1 basis, right? So then we'd get 0 50% of the time and 1 50% of the time. And if we then measured the first qubit, then we get the same answers we did for the temporary qubit, but it still would be like 50-50, right? Like there was still 50% chance of getting 0 and 50% chance of getting 1, and we haven't learned anything about the relative phase we haven't learned anything about whether F0 and F1 are constant.
I see.
So this is actually a specific example of a general phenomenon we're going to talk a lot more later on in the course called decoherence. So the moment any information about what your quantum computer is doing leaks out to anything, some temporary qubit you were using, or just leaks out as like in terms of the state of a photon or anything like that, then it completely screws up your quantum algorithms. And that's really the hard part of building a quantum computer.
Is it like possible to measure in the Bell basis? Is that like a possible thing?
Yes. So yeah. In practice, the way to do a measurement in the Bell basis, or an easy way if you have a quantum computer, is you just apply C0 and then a Hadamard, and that converts the Bell basis into the computational basis. It's a good thing to check. We've sort of we've come close to seeing that various times. But yeah, it's worth, any orthonormal basis you can in principle do a measurement in, but some are more convenient than others, right? On a quantum computer, we normally assume we only know explicitly how to measure in the computational basis, and so we apply unitaries to convert any basis we want into the computational basis.
Then wouldn't this state, like if you measured in the Bell basis, wouldn't you be able to tell if F0 and F1 are different or not?
Yes, no, that's completely true. Okay, but to do that, you have to have access to both the temporary qubit and the input qubit. Okay, if we just haven't kept track of the temporary qubit, we just thought, oh, that was a temporary thing we used, but now we can forget about it, then the circuit won't work. Okay?
Okay.
Okay. So, final comment on Deutsch's problem is that we, 2 is obviously not equal to 1, so we have a quantum speed up, but 2 is equal to order 1, right? We've sped up the thing by like 1 call to this black box function. And really in complexity theory, we don't care the whole lot about the difference between 2 and 1. What we want is some separation in some asymptotic scaling, right? We want to be able to make the input big, and once the growth of the number of calls needed classically and the number of calls needed in quantum mechanics to grow in the asymptotic limit. Okay. And there's a very nice example of an algorithm that lets you do that. It was invented by Bernstein and Bernstein-Vazirani, who is a professor here in EECS. One of the original, the original generation of quantum computing people. The rest of us following on are just the the lesser beings who don't get the fun of creating the field from scratch. And that's the following problem. So what we're wanting to do is we're going to want to determine some bit string that I'm going to call U of length n. Okay. And we're going to try to do that using queries to the black box function fu that takes in an input q that is also a n bit bit string of length n, where f subscript u of q is just u dot q. Okay, so we don't know u. U is a property of this black box function f of u, but what we do is we send q's at it, and it sends back the single bit describing u dot q. This is all mod q, mod 2. Okay, so we send in, say, u might be 101, but we don't know that. We send in 110, and it goes, okay, that's 1.1 is 1, 1.0 is 0, 0.1 is 0. So the whole thing is 1 mod 2. Okay, so each query just gives us a single bit of information. Again, it's easy to see that classically, there are initially 2 to the n possible states. For u, okay? And each call only gives us 1 bit of information. We get a single 0 or 1. So each call can rule out at most 1/2 of the possible states, right? Hence, we need at least order n calls to this black box function to determine u. Is that clear to everyone? Again, we're going to consider quantum mechanical version of the problem, where now we have a unitary that implements f subscript u. And this takes in some thing of n qubits, right? That can store q. And some 1 qubit thing that's going to store the output. And it maps it to q b plus u dot. Okay. So again, this is just a natural quantum black box version of this classical black box. And in this case, we're going to be able to solve it with only 1 call. So this will give us the asymptotic scaling separation that we wanted. Okay. A trick, sort of as before, so we're going to apply UFU to superposition over all possible inputs Q. Okay, and by doing a superposition over all possible inputs simultaneously, we're going to be able to solve the problem. Okay. So here's a question. If I start with a state 0, 0, 0, 0, and n zeros, how do I turn that into a superposition over all possible inputs? It's actually surprisingly easy to do. Anyone got any suggestions?
Apply a Hadamard gate to each qubit.
Awesome. So how would we do it with 1 qubit? We'd just apply a Hadamard, right? And that would take 0 to 0 plus 1. That's the superposition over all qubits. All we're going to do here is apply a Hadamard to each of the n inputs, right? So that's going to give us 1 over square root 2, 0 plus 1, times 1 over square root 2, 0 plus 1, so on, right? If you expand that out, you're going to see that every possible combination of 0, 1, 0, 0, 0, so on is going to show up. And yeah, they're all going to have equal weight and all going to have an equal phase in front of them. So this is just going to equal 2 to the minus n over 2 comes the sum over all possible values of the bit string x times ket x, right? Okay. So then we're going to do the following circuit. You're going to start with all these qubits in the 0 gate state. Okay, I'm just going to use a single line to represent all of these n qubits because we're going to sort of work with them all simultaneously. And going to put the bottom state in state ket 1. Then we're going to apply Hadamards to all the top ones. So that makes it a superposition over all values of x. And we're also going to apply a Hadamard to the output qubit. So let me just fix something. So that's going to make the output qubit be in the minus state, right? And now we're going to apply our big old unitary u f of u. That's going to be our 1 call. Then we're going to apply Hadamards to everything again. And finally, we're going to measure the control qubits. Okay, so just like before, it's going to be the control qubits that actually end up getting the final answer. So So let's track how the state evolves through this process. Okay. Time t1. Can someone tell me what the state is? So what's the state of all the input qubits? Someone? So we've just applied n Hadamard's to all the input qubits and to the output qubits. Okay. So we already said all the input qubits are going to end up just being in a superposition over all inputs x. The output qubit, we had a 1. We applied a Hadamard to it. So it's going to go to 0, -1, the minus state. And finally, this needs to be normalized. So we have a 2 to the minus n plus 1 over 2. It says n plus 1 qubits. Okay. Now, let's look at time t2 after we apply this magic black box function. Okay. So for each x, the first qubit stays unchanged as x. So that doesn't mean that the sort of first qubit, when we look at the whole superposition, is unchanged. But then the second qubit goes to 0 plus x dot u minus 1 plus x dot u. Okay. Again, we're going to use this sort of slightly weird property of the minus state that when you add the same thing, you add x dot u to either both of them or neither of them. That's just the same thing as applying a phase of -1 to the x dot u. So this can be rewritten as 2 to the minus n over 2, sum over x, -1 to the x dot u, x, and then the second qubit is just still in the minus. So even though it seemed like what we were doing was acting on the second qubit, but not the first, again, the second qubit has ended up totally unchanged, but the first qubit has got changed because it's got this phase applied that depends on x. What about at time t3? So now the last thing we're going to do is we're going to apply Hadamard on each of these qubits. Okay. So let's first work out what happens when we apply a Hadamard on every qubit to some bit string x. Right? Can anyone tell me what this is? So if I have some bit string x that consists of 0s and 1s, what are the 0s going to go to? Right, if I apply a Hadamard to a 0, what does it go to? Come on, guys, stop being so quiet.
Plus.
Plus, okay, and what are the 1s going to go to?
Minus.
Awesome. So just like when we applied n copies of Hadamard to 0, we're going to get a superposition over all possible values of y, I'll call it. Right, just because both the plus and the minus states, so no matter what x is, then we get a superposition of 0 and 1, but we also need to keep track of the phases, right? So if some bit in x is 0, then we just don't get any phase. You know, the corresponding qubit of y is just 0 plus 1. right? But if x is 1, then it goes to 0, -1. That means we get a phase of -1 whenever a qubit in x is 1 and the corresponding qubit in y is 1, right? So the whole phase we get in front of some bit string y is just -1 to the x dot y. Okay. So that's going to be useful because we can now apply that in superposition to our state psi. Yeah. I'll write that better. So psi is n Hadamard's applied to 2 to the minus n over 2, sum over x, -1 to the x dot u, x, and then there's this minus sitting there that's just not going to have anything happen to it. Okay, so for each term in that, let's substitute in our answer for what happens to x. So we now have a sum over x and a sum over bit strings y. We still have this -1 to the x dot u. Now also have -1 to the x dot y, y, and a minus. Okay.
I think there should be a different power of 2 up front.
Yeah. Should be 2 to the minus n. Let me actually erase that. Very good point. So we had the 2 to the minus n over 2 already, and we got a new 2 to the minus n over 2 because each x got converted in superposition over things. So the full power is 2 to the minus n. Okay. -1 to the x dot y times -1. So to the x dot u times -1 to the x dot y. It's just -1 to the x dot u plus y. Does anyone know what this is equal to off the top of their head?
Like a delta function?
Yep. So this is actually a problem on your homework, so I'm not going to justify it at all. But it turns out this is 2 to the n times delta uy. Okay, so 0 unless the bit strings u and y are exactly equal. And if so, it's 2 to the n. So magically, the state psi is actually just u minus. Now we measure, and we've learned u. Awesome. So with a single call to this function, we managed to completely determine u, even though it would take us this large number, like n calls, to determine it classically. Moreover, we have solved the problem by trying every possible input at once, right? The thing we put in was a superposition over all inputs to the classical function. We did them all at once by applying the unitary to the superposition, and then we magically got the answer to the question, okay, that otherwise we'd have had to put in all the different inputs. So this is sometimes called quantum parallelism. Okay, this is sort of the pop sci description of how quantum computers work, right? They try everything at once, and then the right answer is the one that comes out, and then they magically work. Okay. However, there's an alternative interpretation of how the Bernstein-Vazirani algorithm works. that is less hopsci and crazy, but sort of more useful in gaining understanding. That's just to think about what this U f of U actually does. Right? So what does this thing do? Well, it adds, U dot Q, okay, to the output bit at the bottom. Another way of doing that same thing would be to just apply some number of C naughts, right? So maybe we apply, let's say the bits of U were the top bit, the second bit, and the last bit were equal to 1, and the third bit was not equal to 1. Then UFU would just look like a circuit that applies a C naught based on the top bit, the second bit, and the bottom bit. Right, so we add 1 to this bottom qubit. If the top bit is 1, i.e., because then that adds 1 to U dot Q. If the second bit is 1, if the last bit is 1. So it's a C naught for each input where UI is equal to 1. Okay. Now let's look at this whole circuit. We have some zeros being input. And a 1 down the bottom. Hadamard here. Hadamard. 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 And then we apply the U f of U, right, which is just some control knots. And then we apply some more Hadamards. Okay. So we have two sorts of bits here. We have the ones where there's no C naught applied at all. In that case, the two Hadamards just cancel out, right? And we have the ones where there is a C naught applied. But in this case, we know the two Hadamards, a C naught with the control bit at the top and the target bit at the bottom is the same as a C naught with a target bit at the top and control bit at the bottom with extra Hadamards sandwiched around it, right? So this circuit is actually equal to a circuit where we just don't have any Hadamards acting on the input bits, and instead we just have C naughts controlled by this bottom bit. And finally, there's an extra Hadamard here because we didn't have a Hadamard here. So just using the same usual tricks we have for flipping the control and target bits of a C naught, then we can see that the circuit is exactly the same as this one. And now it's very obvious, right? This is just in state 1. So these things aren't just acting as NOT gates. So we're just adding a NOT for each input where UI was 1. So it's completely obvious that this output is just going to be U. There's nothing magical going on out at all. And here we just have a minus because we had a 1 and then we applied a Hadamard to it. Okay. So this is a sort of less magical interpretation, where we're not trying everything at once. We're just using the fact that when we switch bases, the control and target bits of the C0 get switched over. And so we're really just applying some C0s to all the bits that are, where U is not equal to 0. Okay. The lesson here is not that the sort of interpretation of you're doing a superposition of everything at once is like wrong as such. The lesson is that that's not sort of how quantum computing works in general. Like I can't just arbitrarily try everything in superposition and then immediately extract the right answer. So if I have a superposition over all sorts of things, then when I do a measurement, I'm only going to get the one I want with some very small, in fact, exponentially small probability. So quantum computers can't just try every possible classical computation at once. That would imply that MP is contained in BQP. This is not thought to be true. Instead, it's thought by experts in the field, by which I really mean Scott Aronson, probably the biggest expert in the field, but there's also others. General consensus is that plenty of problems that are in MP that we can't solve on a quantum computer, but there's also, in fact, some problems can solve on a quantum computer that can't be solved, can't be verified classically in a small amount of time. The classic example of this is just simulating quantum mechanics. It's not thought to be in NP, but it obviously can be done on a quantum computer because that's how a quantum computer works. Also worth noting, just in case it ever comes up, there does exist a quantum version of NP, things that can be verified fast on a quantum computer. This is called QMA. It's not thought to be the same thing as BQP, but that's the last thing I'll say about that. So the actual way Bernstein-Vazirani worked, and the way actual quantum algorithms will work in general, is really 2 steps. You often will like try everything or lots of things in superposition. But then the hard part and the important part of the algorithm is that you need to find some particular trick that for that particular problem lets you extract the right answer. And finding these tricks is in general hard. Very few of them are known. The list of important quantum algorithms is really quite short, much shorter than the list of important classical algorithms. But for Bernstein-Vazirani, for example, the trick was really that by using these by having Hadamard's here as well, after we do apply U of F to the superposition, then we can switch around the target and controlled things at the C naught, and it was the fact that UFU had that particularly simple structure. Okay. In general, there's two important algorithms where you can actually do interesting things. And that's it. Anything else you've heard of is either an application of one of these two things, or it's like a variant on them, or it's like probably doesn't work, or it's some very niche thing. The first involves doing what's called a quantum Fourier transform. Can roughly be thought of a fancier version of what we did in Bernstein-Vazirani, of doing a load of Hadamards. In particular, this is what you do to do Shor's algorithm. This very famous algorithm invented by Peter Shor back in the early 90s that lets you do factoring in polynomial time on a quantum computer. And the second is called Grover search. So the next 3 lectures, we're really going to get into the heart of these things. The next lecture is going to be introducing quantum Fourier transform. Lecture after that, we'll understand how Shor's algorithm works, which has a load of overhead of, a lot of Shor's algorithm involves some like classical tricks to convert the problem of factorizing prime numbers into a problem that you can then input to your classical computer. And then finally in the lecture after that, we're going to talk about Grover search. Okay, I think that is everything. Anyone have any questions?
Yeah, I have a question. So in order to implement the circuit for doing this what's it called, Bernstein-Vazirani algorithm, wouldn't you have to look through every bit of U to connect the C0 gate?
Yep. So this is the setup of Oracle problems, is that you have some circuit that does this, but you imagine that someone else like built it or something like that, right? All you don't know what the circuit does. You don't know like how the physical implementation works. It's like, it's by black box, right? You imagine that it's literally in some box and you can't break open the box. All you can do is feed in inputs and see what the outputs are, right? So certainly if you were able to work out the actual circuit that UFU was implementing, then you can obviously work out U, right? Because you can just work out what the circuit does without actually like calling it.
Yeah, but can't you also do the thing in like OF1 using a classical computer? Say like you encode all the bits of U using classical bits, and then you do, what do you do? You do like an AND with a bunch of ones.
Yeah, so that's a different black box though, right? So there we're getting n bits of n output bits, right? So you're getting to store the output of each of the ones. So the thing you learn is n bits. Okay? In this case, we want the black box. All you're allowed to do, the rules of the game are that you send into the black box some string Q, okay? Or quantum mechanically, you're allowing it to be a superposition over Qs, but classically, you just put in some string Q, and then you get back a single output bit plus your original Qs, I guess, if you want them, which is just U.Q. Okay, you're wanting a different setup where your black box gives you n output bits that are like U and Q for each one. Right. You don't have the key point is that you don't have any idea at all about the inner workings of this black box. maybe you have to send your qubits to me, and then I'll apply the black box and then send them back to you. Okay, is that clear?
Okay.
Yeah, it's a different set of rules to the set of rules where you know, I know the circuit that I'm applying and I apply it. I'm applying something, but I don't know what the thing I'm applying actually is. That's hidden from me. Okay. The advantage of it is really that it makes things easy to prove. So you can actually prove that you can't do better than that classically, because the only thing you're able to learn, you know, there's 2 to the n possibilities initially, and you're only able to like learn 1 bit at a time. So you can just prove that you need to get at least n bits before you can determine u. So yeah, it's great for proving separations, not interesting otherwise. Any other questions before I stop recording?
Are we assuming that the computational cost of using a Hadamard is much less expensive than the Oracle?
Yeah, so again, good question. All we're counting here, like in the definition of query complexity, all you worry about is the number of calls of the Oracle. So you assume everything else you can just do for free. It's just it's a different set of rules to sort of circuit complexity, where every gate gets counted as a cost.
I have one more. For when you have T3, could you explain again how you get from X to Y?
Yep. So T2, our state was a superposition
T3.
over X's. Yeah, I know. I'll get that. So T3, we had this state, which was a superposition over X's. Okay, and then we're going to apply n Hadamards to that superposition over X's. And if I apply n Hadamards to a single X, then I get a superposition over Y's, right? And now by linearity, I can just see what happens when I apply the Hadamards to the superposition over X's. And what I get is for each X, I get that superposition over Y's. So I get a superposition, really, you know, I'm summing over X and Y here, but the only care to the Y's. Is that clear?
So your Y's are also in the 0, 1 basis, right?
Yes, yes. So I'm just taking this line, okay? And then just by linearity, I'm adding up that for all these different values of X and just adding them up together. But it's the same set of Y's that appear regardless of X. So I just have the same size Y's here, and then I have some sum over X's out the front, which I can then just evaluate.
Okay, yeah, that makes sense.
Awesome.
And then just one more. Could you give an example of what a non-deterministic algorithm would be?
Yeah, so a non-deterministic algorithm is this alternative way of defining MP, right? So the way we did it last lecture was involving a verifier who's trying to show in polynomial time that something is true given some extra information. A non-deterministic algorithm is you have a set of possible algorithms and you assume that you chose the luckiest algorithm that for that particular input will give the yes answer fastest. So for example, you might have your set of possible algorithms to just be for the subset sum problem to just try particular subsets and see if they add up to 0. Okay, and there's your set of algorithms is all the possible orders for trying subsets. And now you assume you chose the luckiest one for that particular input, i.e. you chose the one where this first subset you tried adds up to 0. If you did that, if you got that lucky, then you'll be able to answer the question in polynomial time. Okay.
Okay, so it's like kind of like a blind search kind of way of.
It's kind of, but it's more generally, it's just the, yeah, it's whether anybody could work out the answer with confidence, assuming they chose the optimal strategy for that particular input. It's pretty easy to see how it's equivalent to verifying because what the witness information does is it tells you which strategy to try, right? If I have the witness, then I know that I should be trying this particular subset first, but I could have also just got super lucky and that just happened to be the subset that I picked.
Okay, thank you.
Cool. Okay, I think I will stop the recording there.